Swayam Prabha. Digital India. Educated India.
Welcome to this edition of Chemical Reaction Engineering. In this edition, we will be looking at deactivating catalytic systems. And of course, deactivating catalytic systems are not new to us. Chemical process industry has made great strides in this area of catalysis and so on. But our concern here is how do we deal with designs for deactivating catalysts, and then how do we manage systems in which there is catalyst deactivation and so on. So, we will try to go through this in a simple way, so that we get a grip on what happens and so on. So, we will begin, and let us look at this problem of our interest is that we have a catalyst which deactivates, and we want to understand what is the kinetics of catalyst deactivation. Why is this required? It is required because that data would be, that model, the data whatever is useful for us to design systems in which catalyst undergoes deactivation. So, to be able to quantitate a situation like this, what we have got here is a stir tank. There is a stirrer in the, there is a stirrer, and the stirrer has a small basket which contains the catalyst. Okay. Now, this stirrer is spinning. The idea of making it spin so that the temperature and compositions inside the equipment remains reasonably the same everywhere, so that our data can be meaningfully used for other purposes. We have feed coming in at a certain concentration and going out a certain concentration, and that is the reaction that is taking place inside this equipment. And we want to quantitate the extent to which catalyst deactivates. We want to make these measurements so that we can make use of it in other systems design and so on. So, to be able to do this, I have written down the material balance for material coming in, input, its output, V naught C A naught is input, so many moles per time, so many moles per time is going out, and this is the rate at which chemical reaction is occurring, where R A is the rate function, V is the volume of the equipment. In this case, this volume refers to the volume of the catalyst, and this is the accumulation term, which is V times d by dt of C A. I have taken V outside the derivative because V is constant, that is why I have taken it outside, and I have written V naught same at the inlet and the outlet under the assumption that there is not much of volume change, because we are looking at a reaction which is A going to B. Okay. Now, we want to sort of take it forward by doing some simple manipulations. So, I have said this psi is C by C A 0, it is non-dimensional, and I have defined a what is called as a characteristic time, tau d is the characteristic time for deactivation. What is meant by characteristic time? For example, in our commercial processes, our catalysts perhaps last for a year, sometimes for 2 years, while the reaction time, that means the time that these gases spend inside this equipment, and the time that these gases spend inside this equipment is generally quite small. But what is really of great interest to us is what is the time for which the catalyst would last. So, it makes sense for us to be able to look at what happens to this equation in the time scale of deactivation. That time scale is taken as tau d. What is tau d? Tau d is the characteristic time for deactivation. For example, if the catalyst lasts for 1 year, our characteristic time is 1 year. That is the meaning of tau d. So, what we have done here is that we have done non-dimensionalization of chronological time t with respect to the characteristic time for deactivation, that is theta. Okay. So, what we have done, we have defined a variable psi which is C A by C A 0, we have defined a variable theta which is T by tau d. Therefore, we can now write this equation in forms like this 1 minus of psi R A tau r C A 0 tau r by tau d d psi by d theta. What is tau r? Tau r is volume of by V 0. Okay. In this case, this V refers to the volume of catalyst that we have put inside the equipment. Okay. Now, if you look at this equation here, let me go to the next line because that. So, we have the unsteady state representation of our stirred tank. We have our stirred tank here. Okay. Let us not forget our system. We have the stirred tank. Our catalyst is sitting here. Okay. Material is coming in, material is going out due to reaction A going to B. Okay. All right. So, this represents 1 minus of psi R A tau r C A by C A 0 equal to tau r by tau d d psi by d theta is the statement of the unsteady state material balance for the material that is happening inside this reaction equipment. Okay. Now, if you look carefully, what do we find? We find that the order of magnitude of psi is order of magnitude is 1. Why is it 1? Psi is C A by C A 0, at best psi can go to 1, I mean C A by C A 0 can be 1. Therefore, values are roughly of the order of magnitude of 1. If you look at theta, this ratio at best can be 1. So, order of magnitude is 1. Once again, we recognize that R A tau r by C A 0. What is tau r? Tau r is some kind of a reaction time. We can all say the inverse of reaction time is rate constant. Therefore, what this whole thing refers to is that is some kind of a ratio of reaction rate divided by the maximum reaction rate. That is the kind of meaning this gives. Also has an order of magnitude of 1. So, what we are saying is that in this unsteady state representation of the material balance for this stirred tank, all the terms are first term is magnitude 1, order of magnitude 1, order of magnitude 1, order of magnitude 1, order of magnitude 1. Okay, order of magnitude 1. The only thing that is not this tau r by tau d, you see all terms being of the order of magnitude of 1, if any of these terms are very small, we can knock them out. For example, if we find that this term tau r by tau d is very small, then we can knock out this term. Okay. That is the point that we are trying to get across. What we are saying is that under the non-dimensional representation, we are able to look at the values of each term, and since the order of magnitude is all made up to 1, any term which is very small we can knock out, and therefore, we can understand what is happening to the system under those conditions under which this particular assumption holds. Or in other words, in this particular case, tau r by tau d less than 1 means that this right hand side can be knocked out. Therefore, we can look at the material balance as equal to 1 minus of psi R A tau r by C A 0 equal to 0. Since the right hand side is near very small, we call it equal to 0. When this equality becomes 0, we call this as the quasi steady state approximation. Or in other words, what we are trying to say here is that under the condition that tau r by tau d is very small, the accumulation inside the reaction equipment can be neglected. Therefore, we might be able to quite satisfactorily say that 1 minus of psi plus R A times tau r by C A 0 equal to 0. Or in other words, we can say R A equal to 1 minus of psi multiplied by C A 0 divided by tau r. So, what we are trying to say here is the following. Now, here is an instance of a reaction which undergoes a catalyst which undergoes deactivation, which means what? The reaction rates keep on changing because the catalyst is losing its activity. Now, our interest in this whole problem is to be able to measure this catalyst deactivation and quantitate this through a model. This is why we are doing all this experiment. So, what we are saying now is that under conditions where tau r by tau d is very small, the accumulation of material inside the equipment is very small. Therefore, we can neglect it, and therefore, reaction rate R A can be measured simply by measuring the right hand side. Do we know the right hand side? The answer is we know C A 0, we know psi because psi is C A by C A 0, C A is being measured. Tau r, what is tau r? Tau r is simply V by V 0. We have said all these, V by V 0 is tau r, okay, and then psi is Ca by Ca0, and both these are measured quantities, and as a result we are able to measure the reaction rate at any time. Therefore, if the catalyst deactivates, which means the reaction rate keeps changing with time, now we are able to measure what is the reaction rate at any instant of time, because all the points, all the quantities on the right hand side is known. To cut this long story short, what we are trying to say here is, even for the case of a deactivating catalyst, under assumption of quasi steady state, which means that the accumulation inside the equipment is small, we can measure reaction rate simply by measuring psi, which is Ca by Ca0. Ca is measured, Ca0 is measured, tau r is measured, and therefore, all the quantities on the right hand side is known, and therefore, reaction rate is known. Therefore, we are able to quantitate reaction rate as a function of time. This is what we are trying to say. Having said this, so what we are saying now, we have a catalyst, which is deactivating. Now, our interest is to measure how this deactivation is taking place. For doing that, what are we doing? We are measuring reaction rate. How do you measure reaction rate? By measuring all the quantities on the right hand side. What are the quantities on the right hand side? Psi, which is Ca by Ca0, okay, and then tau r, which is V by V0. V is the volume of the catalyst, V is the volumetric flow. Therefore, by measuring the quantities on the right hand side, we are able to measure reaction rate as a function of time. Therefore, the data that is required for us to quantitate catalyst deactivation is in front of us. That is the advantage of what we call as a stirred tank. Stirred tank, as you can see here, this stirred tank, because we are able to put our catalyst inside this basket, we are able to spin it around. We can put it in an equipment, and put our material inside and then take out our material, and by appropriately changing these flow rates, etc., we can measure reaction rates for different conditions of the system of our interest. Okay. Having said this, let us just look at some interesting features that might be of interest to us. Let us say if this reaction of that we are studying, A goes to B, let us say this is a first order reaction. If this is the first order reaction, we know from our basic understanding that the conversion is given by k tau divided by 1 plus k tau. Or in other words, if it is a first order reaction, then our conversion does not depend upon concentration. It only depends upon what is called as the residence time and the reaction rate constant. Okay. That is for a first order reaction. Suppose you have a second order reaction. You notice for a second order reaction, we can do all these. The extent of reaction x depends upon what is the composition at the inlet. It depends upon the composition of that for a PFR. This is for a PFR. This is for a CSTR. This I have written for a CSTR. What I am trying to say here is, we can devise experiments to understand what is the extent to which reaction is occurring. We can measure those reactions depending upon the device. If it is a CSTR, we measure conversion like this. If it is a PFR and a second order reaction, we measure conversion like this. So, depending upon the order of reaction, the dependence of concentration will appear suitably in our expression for conversion, in our expression for rate constant, for the rate of reaction. For example, if you have a PFR and if you have a rate function is k Ca squared as is written here, then the rate function will contain the concentration term in the second part. So, these things we know. The point of trying to draw this attention in this case is that if you have a first order reaction, then there are certain benefits in terms of managing it. If it is second order, then it is a little bit more complicated. I wanted to draw attention to those differences by pointing this out. Okay, let us continue. Let us say we continue with our first order representation for the moment. So, we have a first order reaction in which the catalyst undergoes deactivation. Okay. Now, if you say that this rate of reaction R A is given by K R times C A, where K R is the rate constant, then we know that because of this of the deactivation, this the rate at which chemical reaction occurs changes. It changes because this rate constant is changing with time. You see, that is why we are seeing the effect of the changes in rate constant. Because of that, the reaction velocity is changing. Okay. Now, I have just put it in a slightly different form to make it easier to understand. So, I would put it in this form, R A, which is rate of chemical reaction, is K R times C A, and I have replaced C A in this form because we know all these from our first order understanding. Therefore, the rate at which chemical reaction occurs for a first order process is given by this, and then since the deactivation is occurring, we can now see that the reaction rate at any time, depends on the rate constant K R, which is a function of time, multiplied by C A 0 divided by K R, which is a function of time, multiplied by the residence time. Now, sometimes it is difficult to understand this. Why is rate constant a function of time? The rate constant is function of time is because our rate constant actually consists of a K R 0 multiplied by a term which is called activity. Because of the fact that this activity is a function of time, this product is a function of time. Okay. This is why we see, because this K R is a function of time, because K R 0 is multiplied by this activity which is changing because of the process, we find that the reaction K R is changing with time because A is changing with time, and therefore, the reaction rate is changing with time. Okay. So, what is it that we are saying now? That if you have a catalyst which is deactivating, then reaction rate will change with time. Okay. Our interest in this whole exercise is that can we quantitate and find a model which takes care of this deactivation phenomena. If we can do that, then there are a lot of things that we can do in reactor design, operation, evaluation and so on, which makes the whole thing much easier, and that is the object of this particular module. Okay. So, stating it once again, we are used to stating that reaction rate is K R C A 0 divided by 1 plus K R tau R for a first order reaction, first order in a CSTR. All these are in a CSTR. Okay. So, these are all in a CSTR. Okay. Now, if this reaction is undergoing deactivation, then we recognize that this is going to change with time because K R is going to change with time. So, that is the only. So, these two are representations in which in here we have recognized that the deactivation is occurring, here we have recognized that deactivation is not occurring. See, they are two statements of the same situation. Okay. What are we saying now? What we are saying now is, we have said just now that reaction rate is changing with time. So, we would like to know what is the reaction rate at any time divided by what is the reaction rate at 0 time. So, what is the meaning, what meaning can we attach to reaction rate at any time to reaction rate at 0 time? By definition, it is activity of the catalyst. So, we can say that this is the activity of the catalyst. Okay. The activity of the catalyst is reaction rate at any time divided by reaction rate at 0 time. Okay. Now, just now we derived what is reaction rate at any time, which is this function K R T C A 0 divided by 1 plus K R tau. And what is reaction rate at 0 time? It is 1 plus K R C A K R 0, which means that at 0 time we have taken this K R as K R 0, and therefore, I have written it in this form. So, if I ask you now, this quantity R A, what is the functionality on which this function this A depends? Now, we can tell by looking at the right hand side, that the right hand side depends on number of factors. Very clearly, it depends upon temperature because K R is involved. Okay. Very clearly, we can expect that it depends upon concentration because C A 0 is involved. Okay. Now, we can say since tau R is involved. So, we can in general say that this function, this quantity A depends upon the composition of the system in which the reaction is taking place, which is temperature and composition. Now, that composition is determined by residence time, therefore, it has an indirect dependence on the residence time. Okay. So, what we are trying to say here is that we want to quantitate how activity of the catalyst changes and what is that function which determines this deactivation rate phenomena. So, if you look at the right hand side, if we can measure and quantitate, then we will be able to get A as a function of time in data for which we can model. So, this is what we want to do in this. Let us go further and see what we can do with it. So, let us just look at what is the phenomena we are trying to understand. The phenomena we are trying to understand is what happens to R A as a function of time as C A increases. We know that just looking at, I just write this function once again here, so that we can remember this. We write it here, R A as a function of time is for a first order K R C A 0 divided by 1 plus K R tau R. This is in a CSTR, all these are in a CSTR. So, if you look at this function and say what happens to R A as a function of time as C A increases, you can see very clearly that the reaction rate will increase, therefore, we will get curves like this. Okay. Now, suppose we keep temperature constant C A 0 as constant and you change or increase the residence time, then we will get curves like this, or in other words, for a given one residence time it will be this, for a higher residence time it will be this, another higher residence time it will be this. Okay. Is that clear? Because simply by looking at this expression we can tell what is the direction in which the rate functions will move. Okay. Similarly, when temperature is increased, we will see behavior like this, that at high temperature it will be like this, at lower temperature it will be like this. Okay. So, what we are trying to say now is that if we have a first order reaction, we can measure R A as a function of time, okay, and then we can plot these to understand how the reaction rate is changing with time, okay, and once we do that, then we can measure what is called as activity. What is activity? It is reaction rate at any time divided by reaction rate at 0 time. Okay. Now, moment you do it in this form, you will find that at 0 time all the activity at 0 time should be 1. So, we can actually normalize, the point is that we can normalize the activity as 1, so that we can plot all the data in one curve. So, that is the advantage of this normalization. Is it clear? So, what we have tried to do is that we have tried to conduct an experiment, and this experiment we have done in a CSTR. What is the advantage of doing this in a CSTR? We are able to maintain temperature to the level that we want, and then we are able to change the flow rates or residence time, and therefore, we can measure reaction rate at under different conditions. Now, when we do reaction rate at different conditions, we said that we can normalize the reaction rate at 0 time, okay, and we make plots like this. Okay. What we are saying here is that if you normalize at 0 time, we can say that the activity at 0 time is 1, it's a nomenclature, the activity at 0 time is 1. Then in that case we can plot all of them using the same plot, or we can plot differently as well, that choice is ours. So, what we are trying to say is that we can plot activity as a function of time of our different conditions. Now, having done this, we have activity as a function of time for different conditions. What are the conditions under which we have done the experiment? We have done the experiment for different times, we have done the conditions for different compositions, we have done the experiment for let us say for these two for the moment, okay. And maybe okay, activity was, so our model, we need a model. Let us say that model is this, that the rate at which the activity changes minus of d by dt of dA by dt is this Rd, and the Rd is given by this function Kd times a to the power of m Ca to the power of n. We do not know that function, so we want to find out what is m, what is n, what is Kd. Okay, that is our objective of doing this whole experiment. Now, suppose we find that when we make a plot of A versus time, we get a curve like this, the points like this, we get a curve. Let us say this corresponds to an experiment corresponding to Ca equal to some Ca1. Okay. Now, we repeat this for another set of experiments in which we put Ca equal to some Ca2, then we get, let us say, all these triangles. Let us say Ca equal to Ca3, we get, let us say, all these stars. Okay. Now, when you do experiments under different conditions, okay, let us say this is for one temperature, okay, then we can do for another temperature, okay, we can do for another temperature, let us say it is very sharp, okay. A versus T, okay, some data like this. So, what in essence we are able to do through these experiments is that we are able to get A versus T, and because of this experimental data we are able to determine what is the value of M, what is the value of N, what is the value of Kd at different temperatures. So, what we have got from our experiments, we find Kd, M, N, these. So, our deactivation experiments, essentially what is the experiment? We have done Ra at time t divided by Ra at time 0 and made a plot of A versus time, and we got data okay, at one temperature, maybe this may be at temperature T1 and this may be at temperature T2. Is that clear? So, from the data of A versus T, we fitted this curve to this model and found out Kd, M and N, and then Kd values at one temperature, that is it is Kd1, similarly another temperature we got Kd2, another temperature we got Kd3 and so on. So, in other words, we had value of Kd at different temperatures and M and N. Okay. Is this clear? So, the whole object of doing this CSTR kind of experiments is that CSTR allows you to operate at constant temperature comfortably, and therefore, we are able to make composition measurements comfortably, we are able to make changes in the external environment comfortably, and therefore, we are able to get lot of data which spans a great variety of compositions and temperatures, so that we can fit to this model and find out Kd at different temperatures, find out M and N, and we think, I mean most of the data is suggests that M and N values remain reasonably consistent across all these conditions. Okay. Therefore, we have a value of M, a value of N and a value of Kd for different temperatures. Now, what we normally do is that we look for a dependence of temperature on dependence of Kd on temperature, and this is something that we have learnt from our early chemical kinetics, that rate constants against temperatures typically have an Arrhenius kinds of dependence, and it is not unusual to find this kind of dependence, and then when you fit it to a model like this, we find what is called as the activation energy for deactivation. So, what do we get from these experiments? We are able to find out, because we know the value of Kd at different temperatures, because these measurements have been done at different temperatures, and we have found out the Kd from our fitting. We have plotted Kd versus 1 by T, and we find this kind of linearity, and then from the linearity slope we find out what is Ed, the activation energy for deactivation. So, to cut this long story short, what we have done is the following. What we have done is, we have done an experiment in a CSTR. We have done measurements at different compositions and different temperatures. From that reaction rates at different temperature, different conditions, we have found out normalized that reaction rate with respect to 0 time reaction rate and found out activity as a function of time. From the activity as a function of time data, we have fitted to a model like this and found out the value of M, N and Kd. This Kd is at different temperatures, and then we have plotted this Kd versus 1 by T and found out the activation energy for deactivation. So, that our deactivation experiments gives us what is called as M, N and Ed and Kd0. So, these 4 parameters come from our deactivation experiments. Okay. Now, the question, I mean the reason why we have done all these things is to be able to understand how deactivating catalytic reaction systems perform, number one. Number two, more importantly, can we ensure that in spite of deactivation, our process runs as per design, because after all we have designed it for so many tons per day, and if it does not give us that many tons per day, clearly our economics do not work out for us, and our process equipments that we have put in place are not performing to the optimality that we have designed for. Therefore, our prime interest in looking at catalyst deactivation is to be able to understand them, number one, of course. Number two, to be able to make good use of that information, so that our designs are as per our requirements. Now, we want to address that question by just looking back at what we have done. What we have done, if you recall a little earlier, we said our reaction rate, we did this for the case of CSTR, just see, we wrote this for the case of a CSTR. Okay. We said our reaction rates can be described by Kr Ca0 divided by 1 plus Kr Tr. So, I put a Kr 0 here multiplied by A. So, notice here the Kr 0 times A is our Kr, or in other words this is our Kr that we have been talking about. Now, what we are trying to say here is that if I ask you, I want to keep the left hand side constant irrespective of what happens to the catalyst. So, what is the kind of answer that we can think of? If R A has to remain constant, which means what? Then only our designs will give us the productions that we have designed for. So, left hand side must stay constant, which means what? On the right hand side, the term Kr 0 times A should not change. So, we should have Kr 0 times A should be constant. Only then the reaction rate as a function of time will not change. Only then our equipments will deliver productivity that we have designed for. Or in other words, what we are trying to say here is that in the case of a deactivating catalytic systems, we recognize that the catalyst deactivates, therefore, activity will change. But is it something that we can do to ensure that Kr 0 times A does not change? In other words, can we see what we can do to this product Kr 0 times A, so that Kr 0 times A does not change? A might decrease, but which means what we are trying to say here is that can we increase Kr 0 so that it is able to compensate for the loss of activity. Okay. This is the point that we would like to investigate, understand, and see how best we can integrate these ideas into a design. Let us go forward. What are we saying now? What we are saying now is that our reaction rate Ra, it is changing with time, and this is something that we have to accept, because as the process is running due to variety of factors on the catalyst, sintering maybe coke deposition, maybe poisoning, we do not know, it could be different from different situations, the activity is on the way down. So, in order to be able to annul the effect of decrease in activity, what is being suggested is that if you can keep this Kr times A constant, or in other words, if this product is kept constant, then very clearly, as you can see here, when you can keep this Kr 0 times A constant, or we can keep Kr constant, then clearly the right hand side does not change, and therefore left hand side does not change, therefore our productions will be as per design. In other words, what we are trying to say here is that the strategy for managing deactivation should be that keeping this Kr times A constant. Okay. Moment we do that, we have a way of managing deactivation. Okay. Now, how do we do this? What is being suggested is, if we assume that this A is decaying exponentially, which means what? We are saying that dA by dt equal to Kd times A, therefore, A is decaying exponentially. If A decays exponentially, then we can write Kr times A equal to Kr times E dt, therefore, this must be held constant. How do you keep it constant? We keep it constant by recognizing that Kr, which is the rate constant, which is an Arrhenius Ar 0 times exponential of E by RT, and Kd is given by this expression. Therefore, Kr times A can be written as what I have written here, Ar 0 exponential E by RT and exponential Kdt, where this Kd has an Arrhenius dependence, okay, as mentioned here. So, if you look at the last line here, what we are saying here is that while this term decreases with time because of Kd, this term increases its temperature because it is a very strong function of temperature. If this product has to stay constant, it only means that the effect of temperature on increasing this quantity more than makes up for the effect of decrease in this term because of effect of temperature. Let me state this once again. We know that as temperature rises, as T rises, Kd increases, and also as T rises, Kr also increases. but what seems to be happen in real life is that increase in Kr 0, so Kr 0 because of temperature is generally much larger than the effect of Kd increase in the activity of the catalyst. Or in other words, what we are saying is that when we take temperature from x1 to x2, the increase in this first term, you see this first term increases, second term also decreases, because of rise in temperature, but the increase in the first term compensates for the decrease in the second term, okay, so that the product is kept constant. Okay. Or in other words, what we are trying to say here is that deactivation data that we gather from our experiments gives us deactivation parameters. Similarly, reaction rate data in the absence of catalytic deactivation gives you reaction rate parameters. So, we have reaction rate parameters, we have deactivation parameters. What is being said is that when you increase temperature, the rate constant in the reaction rate system increases. Similarly, when you increase temperature, the rate constant in deactivation also increases. But what is important to recognize is that the effect of increase in the rate constant because of increase in temperature compensates for the decrease in the activity because of the increase in deactivation rate constant, so that the product can be held constant, so that our designs ensures the reaction rate does not change with time. And moment reaction rates do not change with time, then our designs gives us productions that we have designed for, and therefore, our economics and our optimalities etc., that we have taken into account, none of them are affected. We will take an example to illustrate how this is actually achieved and some of the issues that arise from some of these features. So, let me illustrate this through an example. What I want to do now is to illustrate interesting example of catalyst deactivation that we might have to encounter in process design, process evaluation, process optimizations and so on. So, here is an instance of an illustration where you have a PFR, it is a plug flow reactor, I call it PFR. It has a catalyst which deactivates. Okay. Now, here is a separator. What do we have? We have a plug flow reactor and a separator. Now, we have this reaction A going to B. Okay. So, there are A going to be, it is a reversible reaction, therefore, every reaction there is reaction 1 and reaction 2, and the data, basic data is given, activation energy for reaction 1 is given, equilibrium constants are given at 2 temperatures and so on. Now, the situation of our interest is the following. The catalyst deactivates. So, in a process when catalyst is deactivating, that after some time the activity of the catalyst is quite not satisfactory to be able to make good use of the downstream equipment. Therefore, you might want to think about disposing it and buying a fresh batch of catalyst. Okay. Catalyst being expensive, there are processes available in which catalyst can be regenerated, and you might want to see whether a regeneration process can be thought of, so that you can regenerate and use that catalyst. Here is an instance of a problem in which problem statement says that this catalyst deactivates, and then the data on the fresh catalyst and spent catalyst is available, and when you regenerate a spent catalyst, it has certain types of activity. Okay. Now, what is important for us in this particular problem is to find out whether the regeneration process that we have put in place is satisfactory for our economics to be satisfactory, for which some data is given. What is the data given? The data says the following. It says the following, that here is a catalyst, fresh catalyst, spent catalyst, regenerated catalyst, the performance is given. Okay. Now, we are asked to judge whether the regeneration process that we have adopted is good enough to be purchased. Now, whenever you want to evaluate, we must say what is the criteria on which we will judge the regeneration process. The kind of criteria that is suggested in this particular exercise is the following. It says the following. It says the catalyst that we are using in this reactor is proprietary. The catalyst undergoes deactivation and the regeneration process is available, and it says that we can accept the regeneration process if the regenerated catalyst, has 90% activity of fresh catalyst. Okay. What are we saying? What we are saying is that we will accept the regeneration process if the activity of the regenerated catalyst is 90% of fresh catalyst. Alternatively, if the activity of the regenerated catalyst is 2.25 times the activity of the fresh of the spent catalyst, also we will accept the process. So, what is being said is the data that is in front of us, we have to evaluate the data on fresh catalyst, spent catalyst, regenerated catalyst with respect to the two criteria mentioned here, which means what? We must judge the activity of regenerated catalyst, estimate the activity based on the data given and see whether it is 90% of the fresh catalyst, or you can check the activity of regenerated catalyst and see whether it is 2.25 times or more than the activity of spent catalyst. If either of these two criteria are met, we are willing to accept the regeneration process. In other words, what we are trying to say here is that we have to deal with deactivating catalysts in our industry. Okay. So, we need a systematic procedure to evaluate process data. Okay. Now, here is an instance of process data in front of us. Okay. All the data is given to us. Now, we have to set up the design equations to see how shall we evaluate the performance of the catalyst under different conditions that is given in front of us. Okay. So, this is what we want to do now. This is what we want to do now. It means the following, that we have a catalyst which is fresh, performs like this. We have a catalyst which is spent, which performs like this. We have a regenerated catalyst which performs like this. We have to see the three data and advise whether we should buy the regeneration process. If so, why? If not, why not? Okay. This is the kind of questions that we want to answer. Okay. Let us get ahead with this problem. Let us get ahead with this problem. How do we solve this problem? How do we solve this problem? Now, to be able to solve a problem in reactor design, reactor optimization, reactor evaluation and so on, we will have to develop equations that will describe the performance of this equipment. So, this is all. Once we have the equation that describes the performance, then we can answer various kinds of questions. Okay. So, we will go through the algebra that is required to set up the design equation for understanding the performance of this equipment, which is a PFR containing a deactivating catalyst. Let us see how we can do this. So, to do this, so what I have done is, of course, I have done this, drawn the same figure once again, maybe. I mean, so we have this catalyst. I have denoted this as 0, 1, 2, 3, 4. Okay. Now, there are a few things that we can recognize very quickly without losing too much time, that this is a separator. Okay. Separator, this is the reactor. Now, this is pure B. Now, since this is pure B and this is Ca0 is coming in, so we can say that since B is fully recovered, this stream is only Ca0. This is common sense, because B is fully recovered, our reaction is A going to B and B going to A, therefore, this is Ca0. It is something very elementary, nothing very complicated. Now, we can write material balances, at various points. So, I have done just fairly elementary, so this is not difficult to do. So, please notice here, this is 0, this position 1, position 2. Now, we are defining conversion. Conversions are defining with respect to conversion y defined with respect to position 1. What do you mean? What we mean is that if I want conversion at position 2 and our reference is position 1, then I say FA2 equal to FA1 multiplied by 1 minus a Y2. That is what I am saying, that is what I have written. FA2 is FA1 multiplied by 1 minus a Y2. Why is that? That is how we are defining conversion here. Is that clear? Similarly, if I ask you what is FB2, that means what is the amount of B at position 2, we say the FB2 is FA1 times Y2, because whatever A is disappearing, it becomes B. So it is, so FA1 and FA2 and FB2 are FA1 1 minus the Y2 and FA1 1 minus the Y2. If I ask you, please look at this data, it says composition at reactor exit is 25%. So if composition is 25%, means what? This is a gaseous reaction. Therefore, if I find the mole fraction, this is the number of moles at the exit. So if this is mole fraction Y2, so what is this equal to? So this is not Y2. This ratio is equal to this 1 minus FA1 1 minus Y2 divided by FA1. You can see this 2 is FA1. So this is mole fraction. So mole fraction at 2. So mole fraction at 2 is 0.25. That is the data given. Please, this data is given. Okay, this is given here. Therefore, you can find out from this that Y2 value at reactor exit is 0.75. What are we saying? What we are saying is that if I give you mole fraction at position 2, I can calculate conversion simply from these relationships. Therefore, if I say mole fraction is 0.25, then conversion is 0.75. Or in other words, what we are saying is that in this data, mole fraction at the reactor exit is 25%, means our conversion is 75 here. Here it is 32.2, means our conversion is 67.8. In this is 19%, means our conversion is 81%. Okay. So this is the kind of data that is given. Okay. That is what we are saying. So what we are trying to say is we have found a value of Y2, because that is given to us from the data. We have converted the data into value of Y2, so that we can go ahead and doing the evaluation. Okay. Now let us go forward. What we are now saying is, all right, now we know how to make good use of the data. Only we have to write various simple expressions for various flows, so that we can understand what is going on in the equipment. So please once again look at our figures, so that we can understand. What we are saying here is that FA1 is FA0 plus FA4. Please see here, FA1, this is FA1, FA1 is equal to what is coming at 0 and what is coming at 4. So FA1 is FA0 plus FA4. And what is FA4? We know that FA4 is only FA2, because all the 2 here will come to 4. What is FA2? We just now said FA2 equal to FA1 times 1 minus of Y2. We said that just now. Therefore, and similarly, what is coming here? All the 2 that is coming here is also going to come here. Therefore, FA2 is also equal to FA4. This is also equal to FA4. Correct. Therefore, what is coming at position 1 is FA4, which is FA1 times 1 minus of Y2 plus FA0. Therefore, simplifying, you find FA1, that means molar flow at position 1 is simply FA0 divided by Y2. Okay. What we are saying is that from elementary material balance, we find out what is coming at position 1. Okay. Now, what is the concentration of A at position 4? We said all the B is fully recovered, and therefore the concentration at 4 is same as CA0. Okay. So what we are saying now is that CA4 is CA0, and therefore we can calculate now what is the flow at position 4. What is flow at position 4? By definition is FA4 divided by CA4, molar flow divided by concentration. CA4 is CA0, therefore it is FA4 means FA1 times 1 minus the Y2. We have just now said that CA4 is CA0. Therefore we find the molar flow at position 4 is V0 times 1 minus the Y2 divided by Y2. So what we are saying is that molar flow at position 4 we have found out as V0 times 1 minus the Y2 divided by Y2, that is VF4. So what is the molar flow at position 1? V0 plus V4, that is what we have done, V1 equal to V0 plus V4. When you do that, we say it is equal to V0 by Y2. In essence, what we have done is that we have tried to put all the terms that are required for us in terms of quantities that we know from our experiments. Y2 is known from our experiments, V0 is known from our data, V0 is given, Y2 is given. Therefore, we should express all numbers in terms of what we know. That is what we are trying to do in this algebra. Okay, having done that, let's go forward. What we are saying now is that we know from our material balance that concentration at 1 is simply Ca0, because this is also Ca0, we know that Ca1 is Ca0, we know. And what is the concentration at any position? See, after all, if you want to write the design equation for a equipment, we should know concentration at any position. Therefore, we have written what is Ca by definition is Fa by V. What is Fa? Fa1 times 1 minus y at any position. What is V? Since there is no change in volumetric flow, V at any position is V1, which is coming in. Or in other words, what we are saying is that in this PFR, the flow at any position is same as V1, because there is no volume change in the reaction. Okay. And what is the concentration at any position? Fa divided by V. That is what I have written here. Therefore, concentration is Fa by V, which is Ca0 times 1 minus the y for component A, and for B it is Ca0 times y. Therefore, what we have tried to do is that we are now able to express concentrations in terms of y. Okay. Okay. Now, we have expressed all the other flows in terms of known quantities. Therefore, we are now in a position to be able to write the reactor design equation that is required to understand what is going on. So, this is what I have done here. So, our reactor design equation, the d by dV of B is Rb. Therefore, I have written Fb. We know that what is Fb by definition is Fa1 times y. I have written that here. So, Fa1 times d by dV. So, I put all the terms, and notice here that I put 1 inside brackets to indicate that this refers to reaction and not position. So, this is reaction 1, this is reaction 2, and this term is a catalyst activity. This is catalyst activity. What we are saying here is that the reaction rate function Rb depends on K1 alpha times Ca minus K2 alpha times Cb. Notice that the catalyst accelerates both the forward reaction and the reverse reaction. You see. Therefore, we find Fa1 d by dV is given by this expression. So, what we have now been able to do is that we are able to write the design equations for the reactor in terms of y, see dy dV in terms of y, and all other terms excepting y are known. That is the interesting point. That means, we are able to write the design equation in terms of quantities that we know and the quantities we would be able to measure in our experiment. So, this differential equation in this form you can see here Fa0 by y2 dy dV equal to the right hand side. Now, we are able to integrate and then get the results in the form in which we require. When we go further, we recognize that we are able to simplify the equations in terms of numbers that we know. V0 we know, y2 we know. Now, dy dV we can put in terms of beta. Beta is simply k e plus 1 by k, where k e is the equilibrium constant. Therefore, the integrated form of the equation which describes the performance of our equipment is given by this. Okay. Now, see what we have done is that based on our understanding of reaction engineering, we are able to write a design equation which is able to describe our equipment. Notice here that K1 is rate constant for forward reaction, alpha is the activity of the catalyst, V is the volume of catalyst that we have used in our experiment, V0 is the volumetric flow at the inlet, Y2 is the extent of reaction at the reactor exit, beta is simply Ke by Ke plus. So, all the terms we know, see all these are given to us in the experimental data. Our experimental data you can see here very clearly, all these are given to us. Temperature is given, V0 is given, this is V0, this is V0, and what is this? This is actually this is 1 minus of y2 multiplied by 100. So, everything is given, understand. So, 1 minus of y2, we will not write it like this. Okay, this that means if it is 25%, this 0.25, 1 minus of 0.25 is y2. Okay, we know all that. So, what I am trying to say here is that the data that is given can be now utilized to understand how the system is performing, to understand what is the activity of the catalyst, because our question is we are supposed to check the activity of the catalyst and compare with the criteria that is given to us. So, this equation helps us to find out the activity of the catalyst, because all the rest of the quantities are known, and that is the important point of being able to formulate your mathematics, so that you are able to represent the physical system that is in front of you. Now that we know all this, we are now in a position to make an evaluation of the data that is given to us. So, let us evaluate the fresh catalyst. Fresh catalyst, your Y2 is given as 0.75, Y2 is given as 0.75, it is given as 25%, therefore 0.25, 1 minus 0.25 is 0.75. Now beta is Ke plus 1 by Ke, beta values are given. You can see here our equilibrium constant Ke at 450 is given as 8.5, therefore 8.5 plus 1 is 9.5, therefore beta is 1.17 at 450. So, we are able to calculate the value of K1 alpha V at 450, because all the terms on the right hand side, is given, V0 is given, Y2 is given, beta is given, everything is given on the right hand side. You can substitute and calculate the value of the right hand side, which is comes out to be 0.847. So, fresh catalyst K1 alpha V is given as, we have found out as 0.847. Similarly, we can do for a spent catalyst data is also given. So, when you do the same thing for spent catalyst, we find the value for alpha K1V at 477, that turns out to be 0.750, because Y2 is 0.322 is given, and then this value of beta, where is beta values, beta value I have calculated because of the from the data given. So, accordingly we find that the values are 0.678, I have not given the detail here, 0.678 is Y2 and beta is this Ke by Ke plus 1, Ke plus 1 by Ke, which is beta at 477, it turns out to be 7 by 6. Okay, I have done these calculations, the details I have not given here, you can check it for yourself. So, what in essence it means is that at 477 spent catalyst, our value of alpha K1V turns out to be 0.75. For spent catalyst, it is for spent catalyst 0.475, and for fresh catalyst we just now said it is 0.847. We said that just now. Just now we said that fresh catalyst is 0.847. Okay. Now we have to do the same thing for the regenerated catalyst, correct. Now before doing that, let us just go forward a little and find out what is the activity of spent catalyst, because this, notice here that this alpha is at 477. So we always like to express everything in terms of fresh catalyst. So we want to find out the value of alpha at 477, but we want to see what is alpha value with respect to our fresh catalyst. To do that, I have just found out K1 alpha V divided by K1 alpha V 450, this ratio is 0.75 by 0.4, this turns out to be 0.88. So what we are saying is that the value of alpha at 477 divided by value of alpha at 450 is actually what K1 at 450, I just multiplied K1 at 450 divided by K1 at 477, so that I am able to find out what is the activity of catalyst at 477 in relation to activity at 450, and that turns out to be 0.33. What we are trying to say here is the following. What we are trying to say here is that in this experiment, in this catalyst evaluation, we are given a spent catalyst, we want to find out what is the activity of spent catalyst. Okay. Now we find that the spent catalyst is working at 477. Okay. Therefore, we want to check the activity of spent catalyst at 477, and we want to compare this with the activity of the catalyst at 450, and to do that is when we have done this, through this manipulation we have been able to find out what is the activity of spent catalyst at 477 in relation to the activity of the catalyst at 450 by multiplying by the appropriate reaction rates at the two temperatures. That is what I have done. So what we find is that the activity of spent catalyst turns out to be 0.33. So what we are saying here is that spent catalyst with respect to fresh catalyst is quite inactive, and the reason why we are looking at a way of regenerating the catalyst. Let us go forward and look at the activity of regenerated catalyst. Now, the regenerated catalyst data is given at 450. Okay. That in the right hand side all the data is given. When you calculate, we find that K1 alpha V at 450 turns out to be 0.727. Therefore, we can compare the K1 alpha at 450 with fresh catalyst, that turns out to be 0.858. In other words, what we are saying now is that the activity of regenerated catalyst in relation to activity of fresh catalyst, both are at same temperature, it is not 0.9. We said we can accept the regeneration process if the activity is 0.9 or higher. Now, it is only 0.858, and therefore, criteria 1 is not satisfied. So, criteria 1 is not satisfied. Okay. So, that is the first point that we recognize. Now, let us see about criteria 2. What is criteria 2? So, criteria 2 says the activity of regenerated catalyst is 0.858 and activity of spent catalyst is 0.33, and criteria 2 says if it is 2.25 times the activity of spent catalyst, it is okay. If you multiply 0.33 by 2.25, you find that it is less than 0.858. Therefore, criteria 2 is satisfied. Or in other words, what we are trying to say here is that out of the two criteria, criteria 2 is satisfied. Therefore, we can accept the regeneration process. Okay. So, by going through this whole exercise, what we have tried to bring out to your attention is that in a deactivating catalyst will deactivate. Therefore, you are increasing the temperature of operation of the catalyst, and therefore, the spent catalyst, when we are discarding it, the temperature is 477. Okay. What was 450 initially, we had to rise it up to 477 to be able to take care of deactivation. In other words, what we are trying to put across to you here is that in deactivating catalytic systems, increasing the temperature of operation so as to annul the effect of catalyst deactivation is the strategy generally employed. But this strategy may not be successful for the entire duration of operation. You may have to stop it after some time when the activities of the spent of the catalyst is unsatisfactory. You will have to take it out and discard it or replace it by an appropriate regeneration process. Thank you.